Welcome back to Mechanics and Control of Robotic Manipulator. Last class what we have seen inverse kinematic, especially inverse kinematics of some serial manipulator we have seen, a few examples, that is what we have seen. So, this class we are going to add little more. So, what that means? So, you know, like there are two method of solution for finding inverse kinematics. The last class we have seen few numerical example which will give the closed form solution. But today we are going to take a few example which is going to give a numerical method of solution. So, in the sense we are going to use a iterative method. So, if we are actually like seeing there are several iterative methods are possible, but we are going to see one specific method called Newton-Raphson method. So, I will be giving a example with a 2-hour planar serial manipulator, but it is not that actually like restricted to such manipulator, it can be used anything. So, I have chosen this only because I can actually like show it in the pen and paper. So, that is the whole idea. I was actually like you can say taking this 2-hour serial manipulator. So, let us actually like come first what is actually like Newton-Raphson method, then we will be going to the example which we are going to focus. So, if that is the case we can actually like start. So, you know like what we have. So, we have actually like mu is actually like so function of q, right. So, this is actually like given. So, this is what we are actually like found. So, especially like from the you can say transformation matrix of nth with respect to 0, you can actually like found like finally what is your mu. So, mu is actually like nothing but so your end effector positions. Okay. So, then you have actually like end effector orientations. So, this is what mu, but we can actually like generalize and all. So, now if you have this function, can I use any iterative method where I can find if I give mu, can I find q? So, that is the question. So, if I have this big question, numerically there are several ways. So, that is what numerous methods are available to find this q is actually like function of you can say function inverse of mu, but we are actually like taking the iterative because that is more general and it is actually like applicable to any kind of serial or parallel manipulator. In that one of the popular method we call Newton-Raphson method, even some people shortly call Newton's method. So, this is what we are actually like trying to see. So, for seeing that I am actually like trying to show one thing. So, this Newton-Raphson method is actually like mainly come with this. So, if function of x equal to 0, can I actually like find the solution x? So, for that we are actually like taking a plot x versus you can say f of x. Okay. So, now I am actually like trying to show this. So, you can see like this is actually like somewhere like this. Okay. So, this is your function of x and this is actually like with respect to x. So, now you can see like I am taking a random point. I will just complete this. So, I am taking a random point which I say the initial guess. So, this is actually like I call x guess. Okay. So, now, so what I can do, I can actually like make a slope. So, I will just make it this is little more. Okay. So, something like this. So, I am actually like trying to plot. So, I will just because I did not properly make it. Okay. So, now I am taking a guess something like this. This is what my initial guess. Okay. So, which I call x g. Okay. So, now what we are actually like seeing that the slope I can find and the function of x g I can find, the slope I can find, the slope is actually like coming like this. Okay. So, this is the f dash of x g. So, this. So, now what you can see this is actually like ending on the x somewhere, I call something like this is. So, this is g 1 and this is actually like g 2. So, now what I can actually like find, I can find this is actually like going to be 0. Okay. And this is actually like I know. So, in the sense the f dash of x g, how I can write? I can write this is f of x g minus f of okay. So, x g 2 divided by x g 1 minus x g 2, right. So, this way I can find from this what I know x d 1, I want to find out x d 2. So, now if I actually like see here, so what I can see this is another slope will come. Okay. So, you can see. So, now this is actually like giving another you can say iterative point, then I can actually like make a slope. So then that is giving. So like that you keep on going, finally you end up with this point. So this is the basic principle which what you call the Newton-Raphson method is actually like giving. So the same Newton-Raphson method we are actually like going to use for a different benefit. What? So we are actually like going to call, this is what you call mu is function of q. So this is we are going to rewrite as this way, equal to 0. This is what we are going to call as a function of x, where mu is given and we are trying to find out q. What is this with mu is known. So that what we are actually like trying to find. So if that is the case, what is the limitation? The limitation is, so it may not work if there are points are of inflection. So what that means? So if it is actually like inflection, so you have something like this. You take a point here. This may not actually like reach the another point, right? It is actually like come closer here. So now you can see that the original solution. So probably you can see the original solution is somewhere here. So this is what you can see, this is the solution, and you have taken a point here. So this point actually like end up somewhere actually like close here. That is what we are saying, that the inflection point. But the original solution is here. So which even some people call, this is actually like a maxima and this is a minima. This is localized. So if any point is actually like you chosen your initial guess somewhere here, it would be rotating here itself. So that is actually like one of the limitation in the Newton-Raphson method. But still we can actually like try to avoid by providing something, you can say some additional restriction we can do it. So if that is the case, so we can see the same Newton-Raphson method what you have actually like come across in several, you can say numerical methods courses. So we are going to modify that in this course. So what we are trying to say that it is an iterative method, where we are saying that the actual is somewhere, we are actually taking a guess. So the error between these two I am calling actually like delta q. So where q is actually like your joint space variable. So q1 to qn. This qi can be either so theta I or di. Okay. So if it is actually like a rotary joint theta I, if it is a translation joint, it would be joint distance. Okay. So in that sense you have a q vector, that q vector would be in this form. So now we are trying to find out the q vector, but we are taking a guess and actual is something. So we don't know the error, but we assume that this is the error. Okay. Now we want to rectify or go away from this error. For that what we are seeing, so this way you can actually like rewrite this actual as q guess plus delta q. But what we know, we can actually like write delta mu. So the delta mu again you can write this is actual minus mu guess, in the sense, so you know mu is actually like function of q. So you can actually like substitute this guess and then whatever value is coming, that is what mu guess. Okay. And the mu actual is given. So now what you will get? You will get another error called delta mu. So can we relate anything? Yes. So for that what we are trying to do, so we can actually like take the mu actual. So mu actual what? So it is function of q actual, but the q actual is actually like we have written this form, right? So now you substitute this. So what you will get? Q guess plus delta q. So now you can say mu actual in this form and you use a Taylor series of expansion. So what that will give? So that will give actually like function of q guess plus the partial derivative with respect to delta q and the higher order partial derivative multiply with the delta q squared and other things. Okay. So we are actually like assuming that this delta q is very very small. So this all we are actually like making it as 0. Okay. So now what we can actually like see, this is what left, but this is actually like what it is. So you have f is actually like function of q. So this is also vector and this is also vector. So you are taking a differentiation with respect to, you can say vector differentiation with respect to another vector. So obviously that would be end up with what you call partial derivative. So that partial derivative we are getting. So that is what we are actually like finding. So in that sense what you can write, so you can actually like write this is your case, and now you can actually like substitute mu actual in this form. So this will give mu guess and you have mu actual is mu guess plus this. So if you substitute, this 2 will go and only this would be remain, right? So this partial derivative would be in the form of matrix. So that matrix I am calling J of q guess, which is nothing but a Jacobian matrix. Okay. So now in that sense what we have actually like end up with a matrix multiply with the error, but this error we don't know, right? So we are actually like rewriting this equation, and we are actually like rewriting this delta q in the form of this. So now what you have this, right? So now this delta q is what? This is actually like q actual minus q guess, right? So in the sense what you can do, you can actually like make q actual one side and you put it the q guess the other side. So what you will get? So you will get the final solution in this form, right? So now you substitute this here. So what you will actually like get, this is the final equation which we are going to use in the Newton-Raphson method. So now what you can see, so you once you choose the guess, so you have found this is actually like given, you can find k j and then j inverse you can get, and this is actually like mu actual is given, okay, and mu guess you can find because it is function is known to you. So you can actually like get the delta mu and then you can solve the you can say q actual one by one, in the sense iterative method. So that is what we are actually like trying to write. So now you can see that if the forward kinematic solution is available, we can find the inverse kinematic in an iterative manner, where qi is the initial guess, okay, and j of qi is actually like based on the initial guess what is the Jacobian matrix, and this is actually like actual minus your function of q. So this delta mu is obtained, and once you get, you will get I plus 1, then the next iterative that I plus 1 become I and I plus 1 would be new value. Like that you can actually like go iterative and that would be obtainable. So here only condition is you should have this j is supposed to be non, you can say singular, in the sense j of q determinant should be non-zero. Otherwise what happens, this j q inverse would be not possible, okay. So that is what we are actually like writing. So we will take one simple example in the next slide. So for making this as a algorithm, so what we can do, we can actually like start, this is the function, this is available. So we will start with you can say iterative algorithm. So we will start the counter as 0 and we start with the initial guess. So that is what we call actually like qi, that we start, okay. Then we are actually like going with the next step where we calculate Jacobian and Jacobian inverse we calculate, and then we will actually like find this, okay. So once you actually like find this, then we can actually like keep getting it further, and then actually like you can find this particular aspect, okay. So in the sense this delta I can be taken as this function, that you can say the difference in the function inverse actually like obtainable, that you can substitute. So in the sense whatever we have used in the previous slide, that I have rewritten in the form of algorithm. So once you have this, so you can actually like stop. For stopping, we are actually like putting some, you can say, tolerance. So for example, your delta I is actually like very close to 0, then you can stop, need not to be 0, right. So that is what. So how close? So that you need to actually like make your own arrangement. So for that we are taking as a epsilon. So epsilon is your tolerance value. So this epsilon value you can actually like choose, based on that you can actually like restrict this algorithm. For example, you are actually like running in online, so you no need to go the epsilon as 10 power minus 10 and all. You can even restrict 10 power minus 1 is sufficient, you can stop it. So that is the criteria here. So now you can see the same thing what we have written in the equation form, that is written in the form of what you call algorithm. The same algorithm we will try it in a numerical example. So then you will get much more clarity how this algorithm work. In fact, the next lecture I would be showing this in the MATLAB simulation, or you can say MATLAB algorithm base. So we will see. So now let us actually like move the numerical example. For that we are taking a 2R serial manipulator. So we know like this, right. So what would be the x position of this? This is actually like x and y. So this x would be L1 cos theta 1 plus L2 cos theta 1 plus theta 2. So theta 1 is actually like this angle, and the theta 2 is this angle. So we can actually like get this. So similarly y is, so L1 sin theta 1 plus L2 sin, so theta 1 plus theta 2. So now what we are saying, so if we know these two, can I find theta 1 and theta 2 numerically? Yes. So for that, what are the things supposed to be known? This L1 should be known and L2 should be known. These are geometrical parameter, right, which are supposed to be given. So in addition to that, what actually it would be given to you? So it would be like 0 0 and your xy would be given and L1 value would be given, L2 value would be given. So you are actually like trying to fix this in the form so that you can find theta 1 and theta 2, right. So this is what we are trying to do. So for that, what one can do, we can actually like go the forward kinematic model. So this is what I have written. So now you can take the partial derivative, what that means. So dou x by dou theta 1, okay. So dou x by dou theta 2 and dou y by dou theta 1 and dou y by so dou theta 2, right. So this is actually like what you call Jacobian matrix. So you can actually like find. So before that, what one can see, so this is actually like forward kinematic solution is known, and we have already the closed form solution which are already available. So that is what this, just for comparison I am taking this. So this is we have already solved in the last class. So the same solution I have put it here. So now you can see like what we need to know, this Jacobian matrix. So this is we have obtained, and this is the algorithm which is actually like we have formed. So now we are actually like starting with the initial guess, and based on the initial guess we can find the Jacobian inverse and this delta x and delta y, then we can go again, right. So then you can see we are taking one of the numerical example. So where x and y is 1 and 1, in the sense you take this is actually like your x axis and y axis, and this is 0 0. So what you have obtained, so this is so 1 comma 1, okay. In addition to that, what L1 is actually like 1 unit and L2 also 1 unit. So in that sense, what is the best possible solution? So you can easily see the possible solution is, so this is 1 unit and this is 1 unit, right. So L1 and L2 you can fix it, or what you can do, so you can fix it this way, right. So in that sense, theta 1 is 0 and theta 2 is actually like 90 degree is one solution. The other solution is, so theta 1 is 90 degree and theta 2 is minus 90 degree is second solution, okay. So these are the two solutions which we have actually like obtained. So in that sense, so you can see like can we actually like find the same solution in numerical example. So for that, first we are actually like substituting this into the closed form solution which we know. So you substitute L1 and L2 and x and y all are 1. So in the sense this would give 0. So what is S2? S2 is actually like plus or minus square root of 1 minus C2 squared. So that would give plus or minus 1. If you take plus 1, that would give one solution. If you take minus 1, that will give another solution. If you take plus 1, what happened? This is 1 by 0. So in the sense this is actually like infinity. So this will give pi by 2, okay, right. So but it is actually like if you take plus 1, so theta 2 would be so pi by 2. So then theta 1 would be, so tan inverse of 1, this is 5 by 4, and this is actually like what happened, this become, you can say 90. So L2 would be there and here L1 would be there and this would 0. So in the sense what will get 1 by 1, so in the sense minus pi by 4, right. The sense theta 1 is 0, right. If you take it's actually like a minus 1, so then theta 2 would be minus pi by 2. If you take this, this is minus 1. So in the sense it is actually like minus pi by 4. The sense theta 1 is, so pi by 4 minus of minus pi by 4. So in the sense it is actually giving, so pi by 2, okay. So the same solution what we have obtained, this is one solution, okay. So in the sense theta 1 is 0 and theta 2 is actually like pi by 2. So the other solution is this, so theta 1 is pi by 2 and theta 2 is minus pi by 2, right. So both the solution we have obtained. So now we can actually like see the same thing can be obtainable in the numerical basis. So what that means, so you can actually like try to apply the algorithm which we have done. So that we are actually like trying to see, okay. So these are the two solutions. So we are actually like taking into this case. So now what you can see, so you are taking an initial guess. So initial guess can be anything, right. So what can be initial guess? So initial guess I am taking as 60 degree each. So if I substitute this, what I will get? So I'll get delta x something, because so 1 and 1 is given, and this is the mu actual based on this initial guess. Okay. So now this is the difference in the delta mu, this is equal to delta mu, this is the value, and J inverse I need to find. So I substitute that value into, you can say here. So the J value is obtained. So then I can do J inverse, right. So then what I can do, so since J and J inverse are there, so I can go ahead with the algorithm. So I can actually like substitute the J inverse, and the delta mu is obtained, initial guess is there. So I'll get nu, you can say Q I, right. So now based on this, again I will actually like calculate delta, you can say mu, the J inverse, this is delta mu and the initial guess, and then I will get. So like that, if I keep on actually like going it, so what you can see, it is actually like coming closer and closer. You can see, right, this value is actually like getting closer and closer, in the sense getting reduced, and you can see one point of time it is actually like coming. So 1 e power minus 3 ratio, and you can see this is coming, so 10 power minus 10 in the order. So now you can see this is actually like equal. So this is 0 and pi by 2, right. So pi by 2 in radians, if you write, it is 1.57 something, right. So in the sense this is equal. So now we have actually like obtained whatever we have actually like derived it. So now if you are taking, instead of the initial guess is actually like 60 degree and 60 degree, if you are actually taking probably something like 30 and 60, the iterative may be taking time. If you are actually taking 30 and minus 60, it may be ended with the next solution. What is the other solution? It would be actually like pi by 2 and minus pi by 2. Okay. So only one condition I am putting here. So whenever you are substituting, you substitute in the common unit. So you substitute in the radians, okay, because your Jacobian matrix would be in the order different, and you are actually like giving your position values actually like in meter, better you use in radians everywhere. So now these values are in radians, so you can convert that into degrees whenever you require. So with that, we are actually like end up with the Newton-Raphson method. So now the same method can be applied to any serial or parallel manipulator, but this course is actually like restricted to serial. So you can actually like apply for the serial manipulator. So even you can actually like go for 6D of system or 3D of system. It can be RPR or RRR or RPP, whatever manipulator you have, you can actually like apply. So that is one benefit, but one disadvantage, again and again saying that if you are taking a point which is inflection, that may end up with the local region itself. I will show you in the numerical example. Okay. So with that, I am actually like ending this particular lecture. So see you with the numerical example with the MATLAB in upcoming classes. So until then, see you. Thank you. Bye.